And so as we get started here for June 14th, I guess we did post the homework problems that are due for this coming Saturday. That was last Wednesday, those were posted. Do you have any questions at all over those homework problems? And then maybe give me a thumbs up if you've started out on the homework already.
Yeah, I started it. I didn't get quite finished over the weekend, but it seems pretty straightforward.
Perfect. That is a review type deal, but it's good to kind of get back into that mindset. And then there's some new topics in there in regard to thermal effects and those types of things. So I think today I'll go ahead and share my screen. I did review the lecture notes, and we get to cover a lot of material today. It always surprises me when I teach this during a normal academic year. This is probably about 2 to 3 days altogether. I think one thing is it does take a little bit longer to lecture in person as opposed to lecturing here via Zoom, where the notes are already up there. But just looking at the schedule for the summer, it's kind of a lot of information that we cover in a short time frame. And so we really get to cover all the logistics of both statically determinate and statically indeterminate situations today here for torsion. And then we get a look further at different types of cross sections as we go further into the week on Wednesday and Friday. And so this is now, I believe, newer content. Torsion, I don't think, is commonly reached in ME216, or it's just briefly discussed. So this is new stuff. In chapter 5 then, really when you start looking at torsional loading, that routinely occurs in power transmission, where you have the rotation of shafts and transmitting that power that's being developed. Also with rotational machinery, things that are turning, you have to have motors that are turning that, and that's generating a torque. And then also think about tightening of fasteners. You torque those down to a given specification. And so those all develop direct shear or torsional shear stresses in that process. So just think of anything that involves a twisting motion. Shear strain, you can kind of refer to figures 5.1 and 5.2 in your textbook. But the main thing is that there's a linear variation for shear strain from 0 at the center and a maximum gamma max at the maximum radial position for a solid circular shaft. And so if you're to look at that, I thought I had that showing, but that might be figures 5.1 and 5.2. That essentially torsional strain and shear stress develop perpendicular to that twisting motion that develops, and that's going to vary from 0 at the center linearly outward to a maximum at the outer edge. And so there is a distribution of stress and strain through a shaft subjected to torsion. With the nomenclature here, for this, we're generally going to define rho as the radial position, as opposed to R for radius. And so that's what you'll find in the textbook is that radial position value is defined with a rho, and gamma again is our shear strain and maximum at that outer edge. And I'm gonna see, hold on a second, I'm gonna stop sharing. I'm gonna see if I can pull up figures 5.1 and 5.2. I might have those stored for you guys. Yes, let me save this. All right, I'll go ahead and share my screen again. So we can look at this. The figures that are being discussed, kind of just looking at a solid circular shaft before a torsion is applied to that, and then after a torsion is applied or a torque is applied, that's just going to result in that twisting motion. And so I don't think I have the other pictures that I indicated there. And so those will be in your textbook. But that's generally what a torque or torsional loading will do, will cause that twisting motion that will result in a shear strain. And so if we kind of take a look at that concept, realizing that there's going to be that linear distribution, we can really define then the shear strain as a function of that radial position. If it's linearly varying, it's just going to be that radial position over C, that maximum radial position, times gamma max. And that'll make sense if rho is equal to 0, your shear strain will be 0 at that point. If your radial position is equal to C, that maximum radial position, your shear strain will be equal to your maximum shear strain. And so that'll produce just a linearly varying relationship with respect to position for your shear strain. And that's really valid for both circular rods and circular tubes. For a circular tube, your radial position would not be able to be 0. It's going to have some inner radius at that point. And so you would have some finite value of shear strain on the inner wall of a tube, and then that would linearly increase to the maximum shear strain at that outer edge. And so this is our first relationship for our shear strain as a function of position. Then if we look at Hooke's law, our shear stress is equal to our shear modulus times our shear strain. That'll be number 2. Our equation 2. And so if we put equation 2 into equation 1, our shearing strain would be just be the shear stress over the shear modulus equal to rho over C times tau max over our shear modulus. And so G ends up on both sides of the equation, and so they'll just cancel out from one another. if you multiply through both sides by G. And we can see that that same relationship holds true, that the shear stress is a linear function of the radial position, rho over C times tau max. So that's our third relationship. Now looking at the shear stress that develops. And then we can derive that torque and shear stress tau relationship. What is that relationship between the torque and the shear stress? And so if we were to look at torque that's applied, it would really be the integral throughout that area of the radial position times the shear stress times the partial element. And so what you're really looking at there, remember the shear stress times an area would give you a force, times a radial position, force times distance would give you a torque. So that's essentially what we're doing with this integral expression. But we can then make our substitution in here for our shear stress, where our integral is rho times our shear stress, rho over C times tau max dA. And we can then integrate that. Tau max is going to be a constant value. That's the maximum that occurs on that outer edge. C is a constant. That's the outer radius of the shaft. So we can pull those out of the expression, and we end up with the integral of rho squared dA, multiplying the two rho values together. This integral expression is known then as the polar moment of inertia, J. And it's really an object's resistance to torsional deflections. As J increases, things will twist less from that standpoint. And so we'll talk about this polar moment of inertia moving forward. But for now, let's just replace then that integral expression with J. And we can then solve this for the maximum shear stress. So tau max is going to be equal to the torque that's applied times the maximum radial position divided by that polar moment of inertia. And so we're now starting to develop relationships for torsional loading like what we had for axial loading. Axial loading, remember, that was equal to our force that's applied over the cross-sectional area. And now when we start looking at torsion, it's a shear stress that's developed based on the torque that's applied, the radial position, and the polar moment of inertia, which is, again, just geometry factors. Shear stress is a function of the loading that's applied and then geometry factors. But again, this is now a good diagram over here on the right, just showing that linear distribution for a solid circular shaft. A torque is applied. That's just going to cause a twisting motion and a shear stress that develops 0 at the center of the shaft to maximum value at the outer edge. So this is really tau max would be equation 4 there. But if we want to know the shear stress in terms of the radial position, we can just substitute 3 into 4 and see that our shear stress is equal to our torque that's applied times the radial position divided by J. And same thing, this is now that whole linear distribution. And so the shear stress is going to be a maximum when rho is equal to C. From a practical standpoint, it's good to remember that linear distribution occurs, but then oftentimes for design purposes, it's really the maximum shear stress that you're concerned with. So equation 4 is what you often turn to when you're going to the design of a shaft. and you're trying to reach a certain factor of safety. The main thing to be aware of, though, is that equations 4 and 5 are only valid for a circular rod or tube. And we'll talk about that here in a second, about the impact of the polar moment of inertia as we discuss that further. But again, tau is our shear stress. It's a function of rho. Rho is the radial position. C is when rho is equal to the maximum value. Torque, or T, is the torque applied, a unit of force times length. And J is that polar moment of inertia, also called polar second moment of area, but it has units of length to the 4th power, so inches to the 4th, millimeters to the 4th, that type of thing. And then one thing, just to avoid being confused upon that, is that torque does have the same units as work and energy. But torque, the way they do that in the English system, that would be like a pound-foot of torque. Whereas if you're defining energy, it would be in a foot-pound. To avoid confusion, they just alternate those. But I guess you should be aware of, when you're solving problems, if you're dealing with a torque or if you're dealing with energy in your calculations. But they are two significantly different things. Torque is a vector, so it does have a magnitude and direction, whereas work and energy is a scalar. It does not have any direction associated with it. It's just a magnitude. And so just be aware of that. Likewise, when you get into work energy, if you're dealing with the English engineering system, you can start defining that in terms of horsepower. If you're in the SI system, you can define work and energy in terms of the amount of joules that are being used, and then power would be in watts. But those same units you would not use for torque. Those units of joules for work and energy would not be used for torque at all, because joules are only used for work and energy. So now let's get into that polar moment of inertia a little bit more, and dig into that integral and solve that for a circular tube. But J, again, we recalled, is just an integral over the area of rho squared dA. And so now we kind of have to remember back to Calc 3 type stuff. And we can just take you through that. The nice thing is it works out to nice algebraic expressions. So we're typically only on the hook for the algebra expressions. But remember from calculus, I remember doing this in Calc 3, that the integral with respect to the area for a polar coordinate system, dA was equal to r dr d theta. And so here we're just defining rho, or radial position, as equal to r. And so we can make that substitution with r dr d theta, substituting that in with rho. So we have rho squared from up above, and then dA would be equal to a rho d theta for our circular tube. And now when I'm integrating that, then I can put in our outer radius and our inner radius for the outer radius and inner radius of our tube, so that when we're integrating that with respect to position, we're good there. And integrating with respect to theta, doing that from 0 to 2 pi for the full 360 degrees. And so that is your direct application of Calc 3 to looking at the polar moment of inertia for our torsion here. And so that sets up the basic integral relationship. What we can do with that, if we do that first outside integral, there's nothing that is a function of theta. So that would just be a theta term that comes out, and you're substituting in the limits of integration 2 pi, and then subtracting off the lower limit of integration is 0. So you're subtracting off nothing. And so you end up with a 2 pi out of that first integral with respect to theta, and then integrating, then rho squared times rho would give us a rho cubed d rho, and integrating with the limits of r0 to the inner radius. And so now we got a nice easy integral to calculate. The integral of rho cubed with respect to rho would just be a rho to the 4th over 4. 2 pi is still a constant out in front. And so that will cancel. One of the 2's will cancel in the numerator with the 4 in the denominator to leave us with a 2 in the denominator. So that'll give us pi over 2. And then plugging in our limits of integration, we'll have a outer radius to the 4th minus an inner radius to the 4th. And so for a circular tube, the polar moment of inertia then is just pi over 2 times the outer radius to the 4th minus the inner radius to the 4th. So we have a nice algebraic relationship to solve then for our polar moment of inertia. And then remember, this is the outer radius. And so if we put in the outer diameter divided by 2 and that substitution, 2 to the power of 4, 2 times 2 is 4, times another 2 is 8, times another 2 is 16. And that 16 times another 2 would give us 32. And so the 32 would be in the denominator, pi over 32 times the outer diameter to the 4th minus the inner diameter to the 4th. And so again, practical applications, you're going to be measuring the diameter of a tube or solid circular section as opposed to the radius if you're putting a pair of calipers on there to do that measurement. This relationship applies for a solid circular section as well. It would just be that that inner radius or inner diameter is equal to 0. And then just be pi over 2 times the radius to the 4th. That would be the outer radius, or pi over 32 times the outer diameter to the 4th for a solid circular section. All right, and so this is kind of where I want to discuss this a little bit. We see that the shear stress is a function of the torque that's applied times the radial position divided by J. And so J is going to increase as you move material further and further away from that center point of that rotation. If you have the same amount of material, but in a tube and extended way out there, that's going to cause your J value to increase. And so that might be kind of a first thought on, well, shoot, we want low shear stresses, so let's just make this into a really big tube. The problem that comes up is that there's an elastic stability that occurs that can cause the tube to buckle under torsion. And so you can only get away with that so far with dealing with tubes in terms of increasing the radius and moving that material out there, because you'll run into a point where elastic stability is an issue, and it will cause the shaft to buckle under those torsional loads. I was just looking at more pictures that I put in here. This is just showing that twisting motion and again, and how that reduces or creates shearing stress behavior. And then as we start looking at the angle of twist that's being developed, one, a positive torque that is applied, you're just using the right hand rule. So your thumb is facing in the direction of the torque, and then your fingers curl in the direction of that positive angle of twist. And so that's just going to cause things to rotate around. And then if this is fixed on that backside, it's just going to linearly vary along the length of the beam back to 0. And again, same thing there, showing that linear variation of shear stress and dealing with that right hand rule. Next up is that positive sign convention, similar to what we looked at for beams when we looked at the internal force, the transverse shear, and the bending. The main key takeaway here for this figure 515 is just that right hand rule applies. If you take this rod that's in the top figure and you make a cut there, you essentially point your thumb away from the cut on each side, and that will define the positive directions for the torque and the angle of twist. So that angle of twist phi then, just some more relationship pairs. That's going to be a function of the shearing strain, the radial position, the angle of twist, and the length. And then the shear stress, we've defined that as the torque times the radial position divided by J. And then the Hooke's law for shear stress is the shear stress is equal to the shear modulus times the shearing strain. And so if we make those substitutions in, our shear stress is T times the radial position over J, and that's then equal to our shear modulus times our shear strain. And that's going to be rho times our angle of twist divided by L. I believe this figure 515 is kind of showing that effect of that relationship between the shearing strain and that angle of twist. With that being the case, the radial positions cancel out on both sides, and we can solve for the angle of twist being equal to the torque that's applied, the length of that shaft, then divided through by the polar moment of inertia and the shear modulus. And so this angle of twist then would be a unitless value, but it would define a rotation. And so that unitless rotation then would be an angle of radians. And so this is in comparison to what we learned in axial loading, where again, remember that axial stress was sigma equal to P over A. That produces a normal stress. And then the displacement, delta, was equal to PL over EA. And so this is analogous to that. Our angle of twist is referring to then a displacement, an angular displacement with a function of the torque that's applied, the length of the shaft, the geometry parameters with the polar moment of inertia, and that material property, the shear modulus G. Then if you have a shaft that has multiple sections, you can really look at that as a sum and just sum the angle of twist that you would get out of each section. So you would have n number of sections that you're looking at for that. So the phi is the angle of twist in radians, and it really applies to the linear elastic region only for both circular rods and tubes. And so for analysis, you can either one, use the internal torque for each segment of the shaft. When you draw your free body diagram, you can look at reaction forces. You can make cuts along the length of the shaft so you can figure out what your internal torque is. And that you can then use directly with your TC over J formula to calculate your shear stress. And then you can use that directly in your TL over JG to figure out the twist. Second, you can also use the principle of superposition to evaluate the effects of each applied torque through all the segment that torque acts. And so that's a little trickier, but it can make things easier in the process. There you're basing things off the external torque that's applied and looking at the effect of that one external torque on all the segments, and then adding up the effect of another external torque, what that does to those. You really have both approaches. The second approach becomes really useful when you're doing statically indeterminate problems. And so we have example problems today, and so I'll take you through both of those methods, looking at the internal torque versus using the principle of superposition. But main thing again with that right-hand rule that we discussed is that both the torque and angle of twist are positive based on the right-hand rule. You're following the curl of, let's do it this way. You're following the curl with your thumb heading out from the cut and the curl of your fingers defining that positive direction. One thing to be really aware of is I'm right-handed, and so one time I was doing homework or solving a solution, and my right hand was busy doing the analysis, and so I was like, I'll use my left hand. And then I just quickly realized that the left hand does not work for the right hand rule. It's backwards. So had to make use of my right hand on that. But there's a strict convention for the positive definition of the torque and the angle of twist, but then it's a little less clear than on the sign associated with the shear stress. And that depends more on the orientation of the stress element with respect to the stress element that you've chosen in relation to that coordinate axis. And so I drew a little picture here to show that. What we've drawn here is just a solid circular shaft with a torque, a positive torque applied. So we put our thumb out in the X direction and our fingers claw around in that positive torque sense. And then if we look at two stress elements at A and B, we can really look at what effect that has and in relation to the coordinate axes. So if we look at that 2D projection of face A, we'd have our x-axis going to the right, our y-axis up. That torque is going to produce a shear stress down on that right face. And then our arrows would then correspond. And remember, the rule with shear stress is you look on the positive x face. If that's going in the positive y direction, that would be positive shear stress. If it's going in the opposite direction, it'd be a negative shear stress. So this positive torque is resulting in a negative tau xy. The tau xy is because we're on that xy plane. Then when we look at element B, same shaft, our positive x-axis would be to the right, and our positive z-axis would be down for that situation. our torque is still going to cause that downward shear stress as things twist and kind of generate an angle of twist in that direction. So it's going to twist in the same direction as the torque arrow. But in this scenario, when we look at the positive X face, that shear stress is going in the positive Z direction. So this would be a tau XZ stress at B, and it would be a positive value. And so this question kind of came up. It must have been a semester I was teaching ME316 or machine design. But the question came up is, how do you know if it's a tau XY or tau XZ? And then how do you know if it's a positive or negative? And so I kind of updated my earlier lecture notes to make that clearer. Really, the component of stress is dependent upon the frame of reference that you're dealing with and the stress element you're dealing with. And the sign depends on just that orientation, the stress element with the coordinate frame of reference. Does that make sense? Are there any questions on that? This comes into play when we start looking at combined loadings, and we might have, say, both a torsional shear stress and a direct shear stress, or a transverse beam shear stress, all happening at the same point. We really need to know the correct signs on those to see if they sum together with their magnitudes or if they subtract with one another. And so it's good to learn this notation early on so that when we get to combined loadings, we can then combine those stresses properly. If we're dealing with just strictly pure torsion though, we oftentimes just neglect the sign on the shear stress and look at that as a magnitude value when we're sizing the shaft. But it's only except for those combined loading conditions when we're trying to determine the magnitude, the correct magnitude of shear stress based on the torsional shear stress, the transverse beam shear stress, any direct shear stress, so that we can account for those properly. The other thing that is important with respect to sign is really looking at the failure plane. We need to have a correct interpretation of the sign to understand where the failure plane is located. So now we can get into some example problems. We will start out with statically determinate, which means we don't have to know anything about the angle of twist to solve for the internal torque within each segment. And for this first example problem, we're given that we have a brass tube, section AB, that has a shear modulus of 5,600 KSI, is connected to a solid stainless steel rod BC that has a shear modulus of 12,500 KSI. I think we can scroll down. So our segment AB that you see there, the bigger one, is the brass tube, and the BC then is the stainless steel section. The geometry properties of this, section AB has a 5-inch outer diameter and a 2.5-inch inner diameter, whereas BC has a 3.5-inch outer diameter. We have two torques that are applied. Torque 1 is counterclockwise with respect to the x-axis at 70 kip-inch, and torque 2 would be a negative. It's going in the opposite direction of the positive x-axis, so that would be T2 of 30 kip inch. And then what we're asked to find is the maximum shear stress for each segment, and then the angle of twist C relative to A that's fixed. And so oftentimes how that's written then is the twist of C relative to A for that value. The length of each of the shaft segments, 2 feet for AB and 3 feet for BC. And for this, I am going to show you that two methods. The method where we're looking at the internal torques, and we just sum the internal torques, TL over JG, to figure out the angle of twist, versus superposition, where we make use of T1 and T2 in that to solve for the angle of twist. So we'll do both methods here for this first one. But based on internal torque, if we just look at segment BC and do a free body diagram where we cut between B and C, we would have torque 2 that's applied. And what you really want to do is your right hand rule, so that you face your thumb out away from the cut. And so a positive TBC value would be going in that same direction as T2. And it's essentially then a summation of moments about the X direction. Just remember, a torque is essentially a moment that causes a twisting motion. And so we'd have a minus T2 minus a torque BC is equal to 0, which just tells you that torque BC is equal to minus T2, which is minus 30 kip inch. So that's the internal torque for section BC. I think I'm going to draw a diagram of that then. And then if we look at segment AB, if we're again making a cut in this section and we're looking at this right hand side, it would be the same type of figure. Thumb going out to the left, so torque AB would be going around in that manner, clockwise if we're looking in that direction. We'd have T1 going around in a counterclockwise direction and T2 in that clockwise direction. So our free body diagram, we are finding that that's a necessary tool again when we start looking at torsional loadings, and we just have that common consistency of drawing a free body diagram to figure out what our internal loadings are. And so if we sum moments about the X, we have a minus T2 plus a T1 minus TAB, and then we can solve for TAB is equal to T1 minus T2. 70 kip inch minus 30 kip inch will give us a torque AB of 40 kip inch. And so those are just random cuts in that first segment and second segment, and that would be the same throughout. So really for that segment AB, it's a common 40 kip inch positive for that section, and then a negative 30 kip inch for that second segment BC, where torque is in kip inch and X is in inches. And so what we want to do then is solve for the internal stresses, and that was kind of back up here in the problem statement. Find tau max for each segment. And for this first case, I'm just kind of keeping track of sign just to show you that. Well, we can solve JB. The outer diameter was given as 5 inches. The inner diameter was given as 2.5 inches. That's our relationship we just looked at for the polar moment inertia. And that ends up being 57.524 inches to the fourth. For the solid section, that's 3.5 inches. Just pi over 32 times 3.5 to the fourth will give you 14.732 inches to the fourth. And we can calculate the maximum shear stress for the section AB, just TAB times CAB over JAB. Again, C is the distance from the center to the outer edge. And so if the outer diameter is 5 inches, that radius then would be 2.5 inches. That'll give you a shear stress of 1.74 KSI. And then doing the same thing for the stainless steel section, that diameter was 3.5 inches. So the radius C would be 1.75. Let's see, yep, so outer diameter 3.5 inches. And then it's JBC that we just calculated, 14.732 inches to the fourth, will give us a shear stress of minus 3.56 KSI. And again, from an analysis standpoint, if you're trying to size the shaft, it's really that magnitude of stress. The sign is really only relevant in terms of finding that plane of failure. But one main note on this is that you cannot rely on the external torques, T1 and T2, to solve for the internal stresses. You always need to do the free body diagram to figure out what those internal torques are. Because we'll notice that our maximum torque that we applied to this thing was 70 kip inch, but the maximum any of the materials ever sees is 40 kip inch. And based on these stresses, you could then relate these back to the material strengths. The other thing you have to be careful is generally what is provided for a material strength is, say, the uniaxial yield strength. And that does not correlate directly with a shear stress. Materials fail in shear much sooner than they do in axial loading. And so that's the intent of failure theories. How do we account for that, in that materials fail differently in terms of how they're loaded? And so the way your book kind of manages that, they don't discuss failure theories until later on, is instead of using a uniaxial shear stress, they define shear yield stress. So you're able to use that number for calculations if you're needing to find factors of safety. And so, like I said, you tend to look at just the absolute values of those. But remember, the sign depends on the stress element and the coordinate axis. So if you're looking for stress at a point, you still have to draw that stress element with respect to your coordinate axis to determine your appropriate sign for that. And then also your factor of safety depends on the strength for each material. And again, chapter 5 is going to be looking at the shear yield strength, not the uniaxial yield strength. But that's stress. The next thing was figuring out what the displacement of C was relative to A. And so that's just the sum of your TL over JG for both of those. And we'll do that based on the internal torque first. We found the internal torque was 40 kip inch and a minus 30 kip inch. So to do this properly, we do have to keep track of the signs for that angle of twist calculation. And we know that 40 kip inch is valid for that 2 feet of the tube. So 24 inches divided by J, 57.524 inches to the fourth, divided by the 5,600 KSI shear modulus for that brass material. And then for the stainless steel, minus 30 kip inch was the internal torque times its length of 3 feet or 36 inches. Its polar moment of inertia and shear modulus as well. And so what we find is that's a 2.98 times 10 to the minus third minus 5.865 times 10 to the minus third from that second one to give us a net total of minus 2.88 times 10 to the minus third radians. And with that, if we look back at that original problem statement, our torque 2 is going to cause both of these shafts to have an angular twist in the negative direction. And then torque 1 is going to cause shaft AB to come back in the counterclockwise direction. But the net effect is it's still rotating more in the clockwise direction as opposed to counterclockwise. So it's going to rotate in the same direction as T2 shown there. So that was one method based off the internal torques. And we kind of saw how nice that was. If you've already solved for your internal torques based off your free body diagram when you're calculating stresses, it's probably just as easy to do the internal torques since you've solved those. If we base that off superposition, then we can break this up into separate loading conditions. Instead of putting those on there simultaneously, it's really the same effect as applying this T1 alone and looking at the angle of twist that develops along that section AB, plus the effect of applying T2 alone. And that would be the effect of that shear or that torque going through both segments AB and BC. And so this then is then based off the external torques that are applied to solve the angle of twist. And so the twist at C then would be torque 1 times LAB, just this smaller portion. It's not loading at all the second portion BC, minus then, because this is in the negative direction, minus T2 times LAB divided by JG, minus again T2 times LBC times JG. So now we're basing that off the external torques, and that 30 kip inch then goes through both segments. And we end up with that same angle of twist, minus 2.88 times 10 to the minus third radians. And so that's really good to do on your calculator, just to make sure you're comfortable with that using the internal torques and also the external torques. And that gives you the same result. It's just slightly different how you're applying that. When you're applying the internal torques, it's only for that section that you're looking at. External torques, it goes throughout all the segments that it impacts in that process. And so we're about 8 pages into it. I think that is a great location to call for a break and then come back in about 5 minutes to see if we can make it through the other 10 pages. We'll get more into statically indeterminate at that point, but I'm going to go ahead and stop sharing for a second, and I'm also going to stop our recording.